During the autumn of 1770, the people living in East Asia witnessed a dramatic and apocalyptic event. For several days, the skies above the Japanese islands, the Korean peninsula, and the eastern coast of China appeared to be engulfed in flames. The nature and cause of this phenomenon were likely beyond the understanding of those who witnessed it, and its memory endured primarily due to a handful of surviving records that persisted over the centuries following the event. Thanks to our scientific advancements, now we know that it was not a magical or extraterrestrial event, but rather a geomagnetic storm induced by the sun sitting in the center of the solar system. However, what exactly are these storms, and why do they cause beautiful dancing auroras in our atmosphere? Let's find out. A geomagnetic storm is a large disturbance in the Earth's magnetosphere that occurs when energy from the solar wind is exchanged very effectively with the space environment surrounding the Earth. These storms are caused by changes in the solar wind that cause great changes in the currents, plasma, and fields in the Earth's magnetosphere. Solar wind conditions effective for generating geomagnetic storms are sustained, several minutes to several hours, periods of fast solar wind. In simple terms, geomagnetic storms occur when a huge puff of charged particles leave the sun and hit Earth's magnetic field, charging it up with huge amounts of energy. Another disturbance in the solar wind that creates favorable conditions for geomagnetic storms is the high-speed solar wind stream. These streams blow forward the slower solar wind and create co-rotating clouds of plasma, scientifically known as interaction regions. The largest storms result in associated solar coronal mass ejections, in which about 1 billion tons of plasma from the sun, along with its own magnetic field, reach our planet. Coronal mass ejections usually take several days to reach Earth, but some of the most intense storms have been observed to arrive in as little as 18 hours. Not too much time to react. But why do they light up our sky? As this stream of high-energy particles approaches Earth, it meets the Earth's magnetic field. Without the magnetosphere shielding us, the solar wind would blow away Earth's delicate atmosphere, which would have pretty nasty consequences to nearly all life forms on our planet. Although this natural shield blocks most of the solar wind, some ions are briefly trapped in the planet's ring-shaped magnetic regions. These areas within the atmosphere are called the ionosphere and are clustered around the geomagnetic poles of the Earth. These poles represent the tilted axis of the Earth's magnetic field. They are about 1,300 kilometers from the geographic poles, but they move constantly, albeit slowly. In the ionosphere, ions from the solar wind collide with oxygen and nitrogen atoms in the Earth's upper atmosphere. The energy released in these collisions causes a colorful bright halo around the poles we all know as the aurora, or the northern/southern lights. Most of the aurora phenomenon is about 97 to 1,000 kilometers above the Earth's surface. That's exactly why you don't need to be right below the geomagnetic poles to see this beautiful event, and countries like Canada, Iceland, or the Scandinavian nations can enjoy these light shows. The aurora borealis is most active when the solar wind is strongest. The solar wind is usually fairly constant, but the solar weather, the heating and cooling of different parts of the sun, can change daily. Solar flares do not significantly affect us humans on Earth. The Earth's atmosphere and magnetic field act as a shield to protect us from cosmic rays. Instruments can measure the amount of radiation reaching the ground, but even during the strongest solar flares, scientists have observed low levels of radiation. It is mainly astronauts and aviation workers who are at risk. Pilots and flight attendants, who spend a lot of their lives flying in the upper atmosphere, who are much more exposed to the harmful effects of radiation. Research suggests that they are at higher risk of developing cancer. An official warning issued for a major space weather event in October 2003 also warned that people traveling on the route north and south of the 35th parallel were at risk of excessive radiation doses. However, Our technology is not as robust as we are. Satellites and space probes orbiting the Earth outside the protective magnetic field are much more prone to malfunction during geomagnetic storms, as these highly charged particles can damage their internal systems. This can lead to major telecommunications and GPS navigation outages. These storms can increase the density of the upper atmosphere, which can deorbit low-orbiting satellites. For example, last year, Elon Musk's SpaceX lost 40 satellites thanks to a geomagnetic storm. In extreme events, Earth-based power grids and other electric devices can malfunction, which underlines just how fragile our modern life is despite all of our technological inventions in the past centuries. Have you witnessed the aurora? We would love for you to share your experience in the comments section.